Hey everyone, in this exercise I will train a zero-shot multilingual sentiment classifier, and the model I will use for this is Multilingual Universal Sentence Encoder, or also known as MUSE, for feature generation. So this particular model and the paper was published in 2019 and specifically deals with multilingual or cross-lingual situations. So quick points about this MUSE model. So the model is a dual encoder model. One side encodes a query, for example, the question in a question answer task, and the other side encodes all possible candidates, for example, all possible responses to a question answer task. The model then computes a similarity metric between the query encoding and the response encoding. The output of the model is the response most similar to the query. And two architectures were tried as the encoder. One is a regular CNN or convolutional neural network for parameter efficient networks, and the other one is Transormer encoder, but that requires much higher level of resources, computing resources I mean. And here is the original paper, Multilingual Universal Sentence Encoder for Semantic Retrieval. If you are interested, you can just search for it. I will give a link of this paper in the description of the video. Alright, so coming back to our exercise here, the goal is to illustrate the zero-shot classification abilities of multilingual models, where the model is only trained on English dataset and then used to predict non-English data with no further training. And for this exercise, I will use the super popular Yelp polarity dataset, which is a binary sentiment classification dataset with 0 and 1 as the target values. So the dataset will be pulled from Hugging Face Hub. This is the one that I'm talking about. The dataset consists of 560,000 highly polar Yelp reviews for training and 38,000 reviews for testing. So just as usual, this is split between train and test in Hugging Face. So to give the background, the original Yelp reviews take numerical scores from 1 to 5 stars. This dataset is constructed by grouping the 1 and 2 stars reviews into the negative sentiment class and 3 and 4 reviews into the positive sentiment class. So I will do the fine-tuning of the MUSE model on this dataset. And again, talking about the MUSE model, MUSE is a transformer encoding text such that text of two different languages with similar meaning will result in a similar encoding. This is analogous to the way two words with similar meaning and usage will have similar word embeddings. And MUSE supports 16 languages. It was trained on Arabic, Chinese simplified, Chinese traditional, English, French, German, Italian, Japanese, Korean, Dutch, Polish, Portuguese, Spanish, Thai, Turkish, and Russian. And here I will use Tensorflow Hub to load the MUSE model. And the dataset obviously will be pulled from Hugging Face. And for the actual modeling code, I will be using PyTorch Lightning. So coming back to my VS Code, first you need to install your relevant packages, TensorFlow Hub, TensorFlow Text, PyTorch Lightning, datasets, and then import all those standard modules from all these packages. So I'm importing Torch, data loader from Torch, and then from datasets I'm loading load dataset, load metric, etc. Anyway, and about the overall project structure, this is the main notebook where you will be running most of the codes and also see the output. But there are two more Python files. The data loading Python file will have the job of loading all the datasets and doing the basic pre-processing on the dataset, and modeling is where I will be handling the actual building of the model with PyTorch Lightning. And that is the reason you see in this cell here that I'm importing both those files as a module, so that I can use all their classes and methods defined in those two files. And here I am just doing pl.seed everything, so that the results are reproducible. And so pull these universal sentence encoder large from TF Hub. And this is a link to where I'll be pulling this model from TF Hub. So let's quickly go through the overview. The universal sentence encoder encodes text into high dimensional vectors that can be used for text classification, semantic similarity, clustering, and other natural language tasks. The model is trained and optimized for greater than word length text such as sentences, phrases, or short paragraphs. It is trained on a variety of data sources and a variety of tasks with the aim of dynamically accommodating a wide variety of natural language understanding tasks. The input is variable length English text, and the output is a 512 dimensional vector. All right, the universal sentence encoder large model is trained with Transormer encoder. And to learn more about TensorFlow embeddings, okay, so that's all we need to know. And so I am pulling the that model in here in the data loading Python file. You just pass your model URL and then you do hub.load model URL. That's all. With these two lines, the entire model will be loaded. And it is the size of the model is 523 MB, so it's pretty moderate. So let's define some methods to load my models and deal with the vectors. So I will have two utils method here and one class. So first util is this method will just take a list of text and produce a NumPy array of vectors, and the vector is coming after encoding the text. It's a list of string, and it will give me numpy.nd array. Return and specifically I'm returning a NumPy list from here, or NumPy array from here, because I want the vectors to be handled by PyTorch. I just don't want to remain as a TensorFlow tensor, because the whole project will be built with PyTorch Lightning. Okay, and then I need another method. This encoder factory method will take a dict of string and integer, which is labeled to integer mapping, and then return me a batch by batch data of batch embeddings and batch label. Let's write it, and then it will be clear. This is going to be a dict of str. Sorry, it's batch embeddings. Embed text. Label to int. Syntax mismatch here. Okay, so these are my two util methods, and now I'm going to define a class the job of which is to get the data, prepare the data, and set up the original pool data for feeding into the PyTorch Lightning model. Yelp data loader. That's going to inherit from PyTorch Lightning data module. Bad size. And now I just need to define now I need to do prepare data. And this method the job here will be to load only partial subset of the original data from the Yelp polarity review, because otherwise the training will it will load. Let me see, 1 second. So in the original data of Yelp polarity, there is no validation set, only train and test. So what I'm going to do here is during the loading itself, I am going to take only partial part of the data for my test and train and also validation. So I need to split it right during the loading. So load data set Yelp. This is where I'm going to split test 2 percentages here. Next will be 2 percentage, and so this is my test, sorry, and this will be my train and val. Yeah, so what this will do is it uses the first 2% of the train and test sets to train and test respectively, and it uses the last 1% of the training set for validation. And so last 1% of the training set, so this will be train. Yeah. So this is where I'm going to define my label to int. That means I have to enumerate over the label names. Yeah. So on the setup, first I'm going to compute embeddings in batches so that they fit in the GPU's RAM. And here I'm going to use the map function of Hugging Face. I need to set the format to PyTorch Tensor because we are going to use PyTorch Lightning here. Columns are Valdias. Oh, I forgot another argument to set format, which is output of all columns to true. Output all columns here. That is defaults to false. Keep unformatted columns as well in the output as Python objects. Okay, yeah. Okay. Oops. Why so many things are coming? Again, I don't know. And it will take batch size. Okay, and I need to repeat this for building my val data loader and also test data loader. There they are. Okay, so I'm done with data loading. So now back in my Jupyter notebook, I can use that Yelp data loader, that method that we just that class that we just built here, and that's how I get my data. One that is pulling from the Yelp polarity review dataset, and also I prepare my data. And what is prepare data? That's this method that we wrote inside our Yelp data loader class. It will just create this label to int and the encoder, etc. And now here I'm just checking the length of this train validation and set train validation and test, and they are my length of the data. Okay, so now I need to start the actual model building. So the multilingual binary classifier, that's target here, and also it's a zero shot learning because I'm going to apply the same learning on other languages to do the translation by the model. So Lightning module organizes your PyTorch code in 6 sections: computations, train loop, validation loop, test loop, prediction loop, and optimizers, and learning rate schedulers. And that's a kind of architecture that I'm going to build. But I need a model class which will incorporate all these different section or all these different architectures within the same class, and that I'm going to write inside my modeling Python file, this one, and then bring in that model class by just doing this. So let's go to my modeling file. This class as well is going to be inheriting from PyTorch Lightning modules. So okay, so all these are self train accuracy, val accuracy, test accuracy, hidden dim, dropout probability. Yeah. Now learning rate, you can actually reduce it even further, maybe. Because we already saw that's the maximum sequence length acceptable by this model that we are using from TensorFlow Hub. It was clearly written in their documentation. So that's all. I'm setting it at 512. So now I'm building these layers by appending one after another layer on top of each other. And for example, here, based on these conditional dropout probability, I'm adding the dropout layer to the layers. So here. And also note here the very important point that I always mention in all other previous fine-tuning videos as well, that here we are following the same architecture, which is that I'm adding a head to a body. So the body is the base model, and on top of that I am adding these classifier linear layer, which is a head. So that's how my whole model will be built. And that is what is fine-tuning all about. Okay, now I'm going to add some linear layer. Linear, to that I add and what was hidden dims, that's this 768 by 128. So this nn.linear takes the first two arguments as in features and out features, and now that I have given prev dim and h as my in features and out features for the before the next layer, I need to update my previous dim to be the out features. So let's, because I'm going to use these prev dim for the next linear layer. You'll see that in a second. Now again, checking for dropout prob. Yeah. And after the ReLU, come out of that for loop, and here the last linear layer. And 2 because it's a binary classification problem, so our number of classes is 2. Self dot okay. Now the next method is forward. So here X will be a batch of USEM vectors. USEM is our model. Logits. Now configure optimizer. Oops, again unnecessarily it's taking everything. This auto intelligence sometimes is really problematic. Yeah. My optimizer is dot Adam W. So, sorry, just the Adam. Self dot learning weight. Okay. I need a loss function. Which will be readings. Predictions will be from on the logits. I need to get the maximum from the logits across the dimension of 1. So torch.org cross entropy. Logits and y. Return the loss, reds, and y. First, I need to get the output from the compute loss. I can do add batch here because this train accuracy is this one, a load metric accuracy. So we can do add batch on this, and also after that we have to do compute. So add batch, that will take and the next one is reference. Self dot second. Now this is another beautiful feature of PyTorch Lightning, this log dict method, where I can tell the model that during the training to save quite a few things on after each epoch. So this is where I define that the log dict should automatically accumulate and logs at the end of each epoch. Progress bar. I'm going to copy the same structure for both my validation and test step. So here it will be oh, I did not return anything from the function, so I need to return loss. And this also test accuracy. Yeah, I think that's it. All right, now I come back to the Jupyter Notebook, and here so now I can do modeling.model, and that's how I define my model. And then before actually training, I need to start defining a couple of configuration into the checkpoint. I think the sorry. Yes. For file name, that's the way that the model will be saved. That's it. You also need to define the trainer class, pretty important. Lightning.trainer. And definitely I suggest you go and check their official documentation. There's a beautiful many guidelines are written in their documentation. So here, first argument, I need to specify the number of GPU. So I'll be running it in Colab or Kaggle. That's obviously 1. And now finally the training loop with you just pass training.fit, pass the model data.train data loader on which the training will happen, and also the validation data loader on which the loss will be calculated, and that will be monitored. That is because I have mentioned the monitor is val loss, so the loss on validation data set will be monitored. And under the hood, the Lightning trainer class handles the training loop details for you, so you don't have to worry too much. It's much easier compared to regular PyTorch. So it automatically enable or disable the gradients. It runs the training, validation, and test data loaders, and also call the callbacks at the appropriate times. And also it puts the batches and computations on the correct devices. So everything is pretty much taken care of for you by PyTorch Lightning. All right, after running for 15 epochs, this is what I got. That it stopped because maximum epoch of 15 reached. So now I need to validate and test a model. So during and after training, we need a way to evaluate our models to make sure that they're not overfitting while training and generalize well on unseen or real world data. And there are generally 2 stages of evaluation: validation and testing. To some degree, they serve the same purpose to make sure models work on real data, but they have some practical differences. Validation is usually done during training, traditionally after each training epoch. It can be used for hyperparameter optimization or tracking model performance during the training. It's a part of the training process itself. But testing is usually done once we are satisfied with the training and only with the best model selected from the validation metrics. So now that this training and validation metric part is over in the previous cell, now the testing part. And with PyTorch training, you do this trainer.test and you pass your test data loader to the data loaders, and that will produce your very important metric, which is your test accuracy and test loss. So I got my test accuracy at 0.89 and test loss is 0.25. And now finally the inference time. So you get your best model from your model, and this is our model class which was defined in the modeling Python file here. So from your model, you just apply load from checkpoint, and from the checkpoint callbacks, you load your best model path. And that will really load your best model. And this best model now will be needed to do our next step, which is inferencing. Now for this one, for inferencing, I definitely need to define and write another little util function which will do the prediction. But before, note this particular thing, that since we used this model use embeddings, which is a cross-lingual model or multilingual model. So we should be able to predict sentiment for non-English languages as well, because this USEM model was trained on 16 languages, all the 16 languages: Arabic, Chinese simplified, Chinese traditional, English, French, etc. And that's what now we are going to do. So the method that I'm going to write now is going to take as input a list of text which are input text, and the job is to predict the emotion on those text. So this method will convert the text to an embeddings, then pass or feed those embeddings to the best model, and then from the model it will get back its output, and finally the method will return the original text, the predicted label, and also the predicted score. It will take a list of strings. So I just converted the text, got the embeddings from the text. Cross the dimension of 1. The results will be a dict, the value pair. First the original text, and I'll just return the result. Now the most interesting part, just apply these predict method on to predict some example text. So this first English text, I took it from a test set from my data set, which is this Yelp polarity. I just from the test portion of the data set, I just randomly took a positive sentiment score, positive sentiment review by a customer. And so what this is, like any Barnes and Noble, it has a nice comfy cafe and a large selection of books. The staff is very friendly and helpful, etc. And then with the Google Translate, I translated that to German. Because I'm going to pass both these original English and the German to my predict method here as a list of text. And look at this, the prediction from the model is label positive, score 0.998, pretty high, and also the same positive label for the German part, and score is also high, but not as high as the English, but still very, very high. So that's the magic of multilingual or cross-lingual model building. Now I'm going to do another thing, another example here. I'm going to pass English text, when converted the English text to Italian using Google Translate, and also to finish with the Google Translate again. So all of these three texts I pass to the model, and now this time the review is negative. So the text is the inside of the restaurant was not clean at all, and we also did not like their lighting arrangement, too dark. Okay, but here just note another important and interesting part. This Finnish translation, Finnish was not part of the original 16 languages on which these USEM model was trained, but I still wanted to check whether the model can somehow work on the Finnish. So I do again, I just to the predict method I pass all this English, Italian and Finnish, and let's see the prediction. So for all of them, it very correctly predicted negative. For the English, negative score is this. For the Italian, negative score is this. And even very interestingly, for the Finnish translation, it gave me a negative label. The score is also pretty high. Now, obviously, these first two prediction were expected because the model was trained on both the Italian and English language. It's a multilingual model, but we do not have, or I do not have, a very good explanation how this model also worked on Finnish, and some possible reason could be thought of. So one possible explanation is that during the training of USEM, they used a technique called subword units, and so in this case, the USEM's model's tokenization lets the transformer learn which subword units are used across languages. So I can only imagine that the subword unit used in Finnish language are close enough to those in the other 16 languages that the USEM model was trained on. But I have to say that I was actually experimenting quite a bit with few other customer reviews as well. So for this particular review, this Finnish language also has produced a correct labeling, but for few other more confusing kind of customer reviews, this Finnish language translation or the prediction did not work as well. For example, for Italian and English, the model predicted very correctly whether it was negative or positive sentiment, but for the Finnish, when the original review is a little bit confusing, the model could not understand it. So yeah, so that's kind of interesting, but the main point is that the multilingual model USEM worked pretty well for the languages that they were trained on and they were supposed to work. Yeah. So to summarize, what we did in the exercise is we trained a zero-shot multilingual sentiment classifier using this USEM model on our Yelp polarity dataset and got our prediction, and that is looking to be working very correctly. Alright, that pretty much wraps up this video. If you have liked this one, smash the like button. And also do subscribe, because I'm going to do many interesting NLP projects over the coming days and weeks. So see you in the next one. Thank you very much for watching.